Let's explore one of the most vital aspects of power system reliability in utility systems: overcurrent protection. Whether you're in the field, in the control room, or simply curious about how we keep the grid safe and stable, this overview will give you a solid introduction to how overcurrent protection works, why it's essential, and how it's applied in the real world. Imagine a power system quietly energizing homes, factories, or data centers. Everything runs smoothly until something unexpected happens. A tree branch falls, lightning strikes, an animal makes contact, or equipment fails. These events cause abnormal currents to flow. These conditions are known as faults or short circuits. Overcurrent protection is a method used for detecting and isolating the affected area, keeping the rest of the grid safe and operational. Since most faults on overhead circuits are temporary, between 65 and 90%, our goal is to maintain high service continuity. We achieve this by isolating only the faulted segment when a permanent fault occurs, minimizing the impact on the rest of the system. For temporary faults, we rely on automatic reclosing, which gives the fault a chance to clear on its own, especially useful when brief outages are acceptable if it means avoiding a longer interruption. At the core of this approach are two guiding principles: sensitivity and security. Sensitivity ensures we detect faults quickly, even when they are small. Meanwhile, security helps us avoid unnecessary trips so we don't disrupt areas that aren't affected. Let's take a step back and look at how distribution systems are built. Most follow a radial topology, a simple one-way path where power flows from the substation to the customer. This design makes coordination easier. In a radial system, protection starts at the downstream device, typically a fuse. It works back toward the upstream device, usually a larger fuse, a recloser, or a circuit breaker in the substation. And fault current decreases the farther you get from the substation. To protect these systems effectively, it's important to understand three critical current values. First, there's the maximum fault current. This represents the worst-case scenario, the highest level of current that could flow during a fault. Next, we have the minimum fault current, which plays a crucial role in detecting ground faults. And finally, the load current, which is simply the normal operating current that flows when everything is working as expected. But here's the challenge. Protective devices can't tell the difference between load, fault, or inrush current. They just see current. That's why we apply margins, multiplication factors added to pickup values to avoid nuisance tripping during cold load pickup, inrush conditions, and any potential future load growth. We also consider impedance from conductors, transformers, and even the ground. Impedance affects how much current flows during a fault and how far a protective device can see or detect down the line. Now imagine trying to predict how fast a protective device will respond to a fault. That's where time current curves, or TCCs, come in. These graphs show how long a device takes to operate at different current levels. Because protective devices follow inverse time characteristics, the higher the current, the faster they trip. TCCs are essential for coordination. They help ensure the device closest to the fault reacts first, minimizing disruption. By overlaying TCCs from different devices, we can visualize how they interact. If two curves cross, it's a red flag. It means both devices might trip for the same fault, which could lead to unnecessary outages. Fuses are the most common protective devices in utility systems, but they're one-shot devices. once they operate, they need to be replaced. They come in two main types: expulsion fuses, zero-awaiting devices that wait for the current to naturally cross zero before extinguishing the arc. They are simple and cost-effective. Current-limiting fuses, zero-forcing devices that act fast, driving the current to zero within a fraction of a cycle. These are ideal for high fault current areas or sensitive loads like hospitals and industrial plants. Fuse coordination isn't just about current. It also depends on ambient temperature, preload conditions, and pre-damage from previous surges. Imagine a fuse that's been exposed all day to high temperatures, already carrying a significant load, and has experienced past inrush currents or lining transients that partially melt the fuse element. Under those pre-existing conditions, it's more likely for the fuse to blow on the next fault faster than expected. That's why understanding these conditions is critical. It helps us avoid nuisance tripping and ensures the system stays protected without unnecessary interruptions. Now let's talk about reclosers, devices designed to open and close up to 4 times, giving temporary faults a chance to clear with a momentary interruption, without causing a sustained outage and requiring the utility to roll a truck. A typical recloser sequence includes 2 fast trips followed by 2 delayed trips, giving the fault multiple chances to clear. If the fault is still present after this attempt, the recloser goes into lockout. Fast trips act quickly to clear temporary faults. Delayed trips allow time for coordination with downstream devices like fuses. Reclosers come in 2 types: hydraulic reclosers, older mechanical devices using fluid pressure; electronic reclosers, modern programmable units with customizable curves, high current lockout, and precise coordination. These electronic recloser controls are like the brains of the system: flexible, responsive, and smart. This is the equivalent to a relay that will be associated with circuit breaker protection and requires engineering work to determine proper settings. There are 2 key coordination strategies to consider. The first is fuse saving, where the recloser clears the fault before the fuse operates. This approach preserves the fuse and avoids a service call. The second is fuse sacrificing, where the fuse is allowed to operate first. This helps prevent blinking the entire circuit, keeping service more stable for unaffected customers. Each strategy has trade-offs in reliability, cost, and customer experience. At the heart of protection engineering is coordination, making sure the right device operates at the right time. For example, a downline fuse should clear a fault before an upline recloser locks out, ensuring that only the affected segment is isolated. At the same time, a recloser should complete its trip sequence without damaging a source side fuse, maintaining proper coordination and preventing unnecessary outages upstream. To make this work, we use tools like the 75% rule, which shift the fuse's minimum melt curve to account for real-world conditions like ambient temperature, preload, and pre-damage. It's a way of building in a safety buffer. For current-limiting fuses, coordination is even faster, under 0.01 seconds. Instead of TCCs, we use I2T energy values to ensure the downline fuse clears the fault before the upline fuse even begins to melt. It's a race against time, and every microsecond counts. Overcurrent protection is both a science and an art. It demands a deep understanding of how electrical systems behave, how faults occur, and how each protective device responds. When we apply principles like sensitivity, security, and coordination, we're not just protecting equipment. We're building systems that are safe, reliable, and resilient. If you'd like to learn more about overcurrent protection in utility systems, contact us or your local Eaton representative to schedule a visit to one of our Power Systems Experience Centers today.